Hi, today we're going to see how to generate an impulse response for Reverb from basically any kind of data like stock market numbers, lottery draws, or temperature curves, for example. To illustrate, I will use the Raman spectrum data from a mineral called Tuctupite. The process I'm going to describe is done with Scilab, but you could totally do the same thing with a Python script. You'll find the Scilab script in the description below. If you're interested in a Python script, please let me know in the comments. So, I grabbed the spectrum data of Tuctupite, which comes as a text file with numerical values. Then I take those values and map them to frequencies from 0 to 20 kHz. I make sure the base data is always positive so we can create a proper frequency spectrum. Mapping from 0 to 20 kHz is totally arbitrary. I could have used another maximal frequency. Next, I use an algorithm called the inverse fast Fourier transform, or IFFT, to turn the frequency spectrum into a time domain signal. You can see this in software like Faceplant in the wavetable editor. It's what lets you see the waveform when you tweak spectral lines. So I get a short time domain signal, about 60 milliseconds. The length depends on how many points are in the data I got. The more points I have, the longer my impulse response will be. Here I have about 2000 points. Once the waveform is created, I center it around 0 and scale its amplitude between minus and plus 1, so it doesn't clip when exported as a wave file. Now we're going to check in Reaper that my impulse response matches the one generated by the IFFT in Scilab. To make sure I have the same frequency data, I will analyze its spectrum with M-Analyzer and compare it to the frequency spectrum I originally created in Scilab. The amplitude scale is in decibels for the top figure and in linear amplitude for the bottom right figure. I can see that the frequency peaks are in the right places, which is great. However, there are more dips in the theoretical curves, and they are not located at the same frequencies as the original. Even though spectrum analyzers tend to smooth what we see in the frequency domain, there is a reason for this noticeable difference. It comes from the fact that the IFFT requires complex numbers as input to work correctly. Simply put, a complex number contains both amplitude and phase information. If I send complex data into the IFFT, I guarantee a time domain signal with the same frequency spectrum. If I only send positive data, the phase information is missing. This results in differences in the dips of the frequency spectrum. Zooming in on the waveform, I notice that the useful signal of the impulse response is very short, around 5 milliseconds. Now, we're going to use this impulse response to generate a reverb. For this, I'm using a free convolution reverb called Convolugy XT. I select the Tuctupite impulse response, set the mix to 0 and gradually bring it up. And I'll play a sample of rain to test it. So, since this impulse response is short, it feels more like a filtering effect than a true reverb. To get more of a reverb effect, we will stretch the sample a bit and also reduce the initial peak of the impulse response. This way, less of the original dry signal comes through. Now it feels more like a box resonance. Even though the impulse response is short, it's already usable. Awesome! As an example, I will try several impulse responses from different sources. A lottery draw, and I leave the stretch at 4 times. It produces something very tonal. An impulse response from the CAC 40, which is a French stock market index. and one from the SBF 120, which is another stock index. We get something tonal and dronic. In this video, we saw the process to generate an impulse response from numerical data using the IFFT. Mapping from 0 to 20 kHz is totally arbitrary. You could map from 500 to 1 kHz instead, or whatever. The IFFT here is approximate because I'm not using complex numbers, but only positive values. The important thing is that the final impulse response resembles the original data and can be used directly in a convolution reverb. This is a first step into impulse response design, how to create and tweak impulse responses to get unconventional reverb textures and understand the parameters that affect sound. Thanks for watching until the end. Take care and bye-bye.